Welcome to day 9. We've built strong technical foundations over the past week. Today, we explore one of AI's most impressive and transformative capabilities, generative AI. Generative models can write human-like text, generate photorealistic images, compose music, and create videos. They represent a quantum leap in AI capabilities and are reshaping how we work, create, and interact with technology. Today, we'll explore the journey of generative models from GANs and VAEs to modern diffusion models and large language models. We'll understand how GANs use adversarial training to generate realistic data. We'll learn how VAEs combine neural networks with probabilistic modeling. We'll dive into diffusion models that gradually transform noise into data. Most importantly, we'll master large language models, the technology behind ChatGPT that has captured public imagination. Here's exactly what we'll accomplish today in generative AI, building on our deep learning knowledge from day 4. First, we'll understand fundamental differences between generative and discriminative approaches. Discriminative models learn boundaries. Generative models learn distributions. Different strategies, different strengths. Second, we'll master generative adversarial networks, where two networks compete. The generator creates fake data trying to fool the discriminator. The discriminator distinguishes real from fake. This competition drives both to improve. Third, we'll learn variational autoencoders that combine neural networks with probabilistic modeling. They learn to encode data into latent spaces and decode from latent samples. Fourth, we'll explore diffusion models that gradually transform noise into structured data through iterative denoising. They've achieved state-of-the-art generation quality. Fifth, and most importantly, we'll deeply understand large language models. How do they work? Why does scale matter so much? What emergent abilities appear? How do we prompt them effectively? After today, you'll understand the technology reshaping industries and society. You'll see why these models are so powerful and their current limitations. Let's clarify fundamental concepts in machine learning that distinguish these paradigms. Discriminative models learn P, Y, X, the probability of the label given the input. They optimize decision boundaries between classes. Traditional supervised learning is discriminative. You have labeled examples, learn to classify. The model doesn't need to understand the full data distribution, just decision boundaries. Discriminative models are typically data efficient and fast to train. Generative models learn PX, the probability distribution of data itself. They learn patterns, structures, and relationships throughout the data. Because they model the full distribution, they can generate new samples by sampling from learned distribution. They can also compute conditional probabilities P, Y, X, that's P, X, Y, P, Y, P, X, though they're typically less efficient for classification than discriminative models. Trade-offs. Generative models are harder to train and require more data, but they enable generation, imputation of missing data, unsupervised learning, and simulation. Discriminative models are easier but less flexible. In practice, we use both. Modern systems often combine approaches, generative pre-training followed by discriminative fine-tuning. GANs use game theory and competition to learn generation. Let me explain the elegant and powerful architecture. The generator G takes random noise as input and outputs fake data samples. Early training produces garbage, but G learns. The discriminator D receives both real data and fake data from G. Its job, classify each as real or fake. During training, D learns to distinguish real from fake. But here's the genius. Both networks improve simultaneously through adversarial training. The generator wants to fool D, generate samples so realistic D can't tell them apart. The discriminator wants to catch fakes, correctly identify all samples. They push each other. G makes better fakes. D learns to distinguish better. G makes even better fakes. At equilibrium, the generator produces samples indistinguishable from real data. The discriminator's accuracy reaches 50% random chance because it truly can't tell real from fake. The generator has learned the data distribution. The challenge? This equilibrium is unstable. Training often fails. Mode collapse occurs where G generates limited variety. Gradient vanishing makes learning difficult. Modern GANs use tricks, spectral normalization, progressive growing, Wasserstein distance to stabilize training. VAEs take a different approach using probabilistic modeling. They learn to encode data into a structured latent space, then decode from samples. Standard autoencoders map data to fixed point in latent space. VAEs map to distributions. During encoding, output means and variances. During decoding, sample from these distributions, then reconstruct. This adds randomness and ensures latent space follows known distribution. The loss has two terms balancing two objectives. Reconstruction loss measures how well we reconstruct original data from latent sample. KL divergence regularization term ensures latent space stays close to standard Gaussian distribution. This balance is crucial. Pure reconstruction creates disconnected data-specific regions in latent space. Pure regularization doesn't reconstruct well. The balance gives a latent space that's both useful for reconstruction and well-behaved for generation. To generate new samples, sample from Gaussian latent space pass through decoder. Unlike GANs, training is stable and deterministic. Unlike GANs, generated images are typically blurrier. But VAEs are more reliable for many applications. They also enable interpolation, blend between two data points through latent space. Diffusion models use a clever approach. Learn to reverse a noise addition process. The forward process is fixed and simple. Start with data, add small Gaussian noise, repeat slightly noisier, continue until pure noise. The forward process is deterministic and well understood. Now, learn the reverse. Start with noise, remove small amount of noise. Repeat, denoise stepwise until reaching original data. Why this works? During training, we observe noisy data and learn to predict the noise added in forward process. At each step, predict what noise was added. By subtracting predicted noise, we denoise. The model learns a denoising network, essentially learning to reverse diffusion. To generate, start with random noise. Apply learned denoising iteratively. Each step removes some noise. After many iterations, you have generated data. This is slower than GAN one-shot generation, but produces higher quality images. Training is more stable than GANs. The process is interpretable. You can visualize progressive denoising. Recent advances like denoising diffusion probabilistic models, DDPMs, and latent diffusion models have made this practical. Stable Diffusion and DALL-E use diffusion-based approaches. They've achieved state-of-the-art image generation quality. Large language models represent a new paradigm enabled by scale. They're essentially scaled-up transformer decoders trained on internet-scale diverse text. How they work? Predict the next word, token given previous tokens. During training, the model sees sequences of text. Compute probability distribution over next tokens. Update parameters to increase probability of actual next token. This simple objective, repeated on billions of examples, produces remarkably capable systems. Why scale matters so dramatically? We thought this approach had limits. Scaling from millions to billions of parameters seemed like more of the same. Instead, new abilities emerged. GPT-2 had impressive text generation. GPT-3 could write code, solve reasoning problems, generate creative content. GPT-4 goes further. These emergent abilities are surprising and not fully understood. Emergent abilities: writing code without being trained on coding tasks, mathematical reasoning, translation without translation training. Few-shot learning: learn from examples in the prompt itself. These weren't explicitly trained but emerged from predicting text at massive scale on diverse data. These are foundation models, capable general-purpose systems adaptable to many tasks through prompting rather than retraining. One of the most important discoveries in recent AI is that performance scales predictably. Researchers found that loss follows power laws with respect to compute. More compute generally means better performance. But the relationship is nuanced. You can scale in different ways: more parameters, more training data, longer training. How you allocate compute matters. The Chinchilla paper 2022 showed that allocating compute equally to parameters and data often works better than previous approaches of massive parameters with limited training data. GPT-3 was over-parameterized relative to data. Chinchilla optimal models achieve better performance per compute unit. What's remarkable? As models scale, qualitatively different behaviors emerge. At small scales, models are poor at reasoning and few-shot learning. At intermediate scales, performance gradually improves. At large scales, new abilities suddenly appear. Few-shot learning works, complex reasoning works, code generation works. These aren't gradual improvements, their emergent abilities absent in smaller models. This emergence is one of AI's biggest open questions. Why do larger models develop new abilities? Is it simply capacity? Is it related to training dynamics? Understanding this is crucial for predicting future capabilities and limitations. One of the most fascinating aspects of large models is emergent abilities, capabilities present in large models but absent in smaller ones. At smaller scales, millions to billions of parameters, models are good at next token prediction for common patterns but fail at reasoning. With intermediate scaling, performance gradually improves. With large scaling, hundreds of billions, qualitatively new abilities emerge. In-context learning is one such ability. The model learns tasks from examples provided in the prompt. Show a few examples of a pattern. The model understands and continues it. This happens without parameter updates, purely from the context provided. Smaller models fail at this completely. Chain of thought prompting reveals another ability. Asking for step-by-step reasoning dramatically improves performance. Without prompting for reasoning, models make mistakes. By asking them to think through problems, accuracy improves. This suggests the model has reasoning capability but needs to be prompted to use it. Few shot learning, provide examples, the model adapts. Zero shot, no examples, just describe the task. Both work surprisingly well for large models. These abilities enable tremendous flexibility. One model can do many tasks through different prompts. These emergent abilities are not well understood. They suggest models learn rich representations of language, concepts, and reasoning during training. Understanding emergence is crucial for predicting future capabilities. Prompt engineering is becoming a core skill for working with large language models. It's the practice of crafting inputs to extract desired outputs. Few short examples are powerful. Show the model a few examples of what you want. It learns the pattern. For classification, show examples of each class. The model infers the pattern and applies it to new examples. No fine-tuning needed. Chain of thought prompting. Ask the model to show its reasoning. Instead of asking for final answer, ask for step-by-step reasoning. Surprisingly, this improves performance dramatically. By forcing explicit reasoning steps, the model gets it right more often. This suggests models have reasoning capability but need prompting to use it. Role specification. Tell the model what role to play. You are a helpful assistant. You are a programming expert. The role shapes responses. More specific roles often elicit better outputs. Clear instructions. Be explicit about requirements. What should the model do? What constraints exist? Should it ask clarifying questions? Explicit instructions reduce misinterpretation. Output formatting. Specify desired output structure. Return JSON. Use bullet points. Write exactly 3 sentences. Formatting constraints help the model match your needs. Prompt engineering is empirical. What works varies by task and model, but these principles are generally useful for extracting capability from large language models. Multimodal models connect different types of data, images, text, audio. They learn unified representations capturing concepts across modalities. CLIP, contrastive language image pre-training, learns to align images and text in shared space. Image of a dog and caption, a dog, get similar embeddings. Random image and caption get different embeddings. By learning this alignment on billions of image caption pairs, CLIP learns what makes images and descriptions match. This enables zero-shot capabilities. Describe what you want to find. CLIP finds matching images without being trained on that specific image class. Describe a concept in text. CLIP identifies images matching that concept. Text-to-image models like DALL-E and Stable Diffusion work differently. Learn to generate images matching text descriptions. Start with noise. Iteratively generate until the generated image matches the text description. This requires understanding both image generation and language understanding. Vision language models like LLaVA and GPT-4V understand both images and text, can answer questions about images, describe images, reason about visual content. Multimodal models demonstrate that different modalities share structure. Learning representations in unified spaces enables transfer across modalities. These capabilities are creating new interfaces and applications, from better search to image editing to accessibility. There are 2 paradigms for adapting models to specific tasks, each with trade-offs. Fine-tuning is the traditional approach. You have task-specific labeled data. Train the model on this data, updating all parameters. The model learns task-specific patterns. Fine-tuning works well when you have sufficient labeled data and computational resources. It can achieve excellent performance. Prompting is newer, enabled by large models' in-context learning abilities. No parameter updates. Instead, craft prompts that guide the model toward desired behavior. Show examples, specify requirements, describe the task. The model adapts based on the prompt context. Trade-offs. Fine-tuning requires labeled data collection and computational resources for training, but when abundant task data exists and extreme performance is needed, fine-tuning works well. Prompting requires no task-specific data collection or training. It's flexible. Change the prompt for different variations of a task, but it may not match fine-tuned performance for complex tasks. The trend with modern large models. Prompting is preferred. Why? Ease of use. No training pipeline needed. Flexibility, one model, many tasks. Speed, instant deployment. As models get larger, prompting becomes more powerful. GPT-3 prompting often matches fine-tuned models. GPT-4 prompting is remarkably capable. Both approaches have value. For rapid prototyping and diverse tasks, prompting. For performance-critical applications with abundant data, consider fine-tuning. Despite impressive capabilities, large language models have important limitations users must understand. Hallucinations are perhaps the most significant challenge. Models generate plausible sounding but false information confidently. They might cite non-existent sources, make up facts, or invent details. This is particularly problematic for factual domains like medicine, law, or science, where accuracy is critical. Users cannot trust everything a model says without verification. Outdated knowledge. Training data has a cutoff date. GPT-3's knowledge cut off in 2021. Models don't know about recent events. They can't browse the internet or access real-time information. This limits utility for time-sensitive applications. Reasoning limitations. While models demonstrate some reasoning ability, they struggle with multi-step logical problems. They fail on novel problem solving requiring true understanding. They can appear to reason, but are often pattern matching rather than deeply reasoning. Bias and fairness. Models reflect biases in training data. They can amplify historical biases and generate unfair outputs. Mitigation requires careful data curation and monitoring. Interpretability. Why did the model generate this specific output? Hard to explain. The model is a black box. This limits use in high-stakes decision-making requiring explainability. These limitations matter. Responsible deployment requires acknowledging them, setting appropriate expectations, and using models where they're suitable. Generative AI is finding applications across industries, creating value and transforming work. Content creation, writers use AI to overcome writer's block, generate first drafts, brainstorm ideas. Designers use text-to-image models to visualize concepts. Musicians experiment with AI composition. Marketing teams generate copy variations, code generation, GitHub Copilot, and similar tools autocomplete code. They understand context and suggest relevant completions. This speeds development and reduces drudgery. AI generates entire functions, not just individual lines. Customer service, chatbots using large language models handle customer inquiries. They understand context, generate human-like responses, handle multiple languages. This reduces human workload on routine questions. Scientific research. Generative models help generate research hypotheses. Text-to-image models visualize concepts. Models analyze research papers, identify patterns, suggest next directions. In materials, science, and drug discovery, generative models design candidate molecules. Personalization. Recommendation systems become more sophisticated using generative AI. Content curation, email, personalization, product suggestions all benefit. The trend. Generative AI is becoming infrastructure. Most future applications will incorporate generative capabilities. Understanding these systems is increasingly important for any AI practitioner. Tomorrow is day 10. Specialized AI applications. We move from generative AI to seeing how AI transforms specific domains. We'll explore healthcare AI, diagnostic systems, medical imaging analysis, drug discovery acceleration. We'll study autonomous vehicles, perception, planning, decision making in complex environments. We'll examine financial AI, trading algorithms, fraud detection, risk assessment. We'll see scientific AI from AlphaFold predicting protein structures to materials science optimization. Each domain has unique challenges. Healthcare requires extreme reliability and explainability. Autonomous vehicles must ensure safety. Finance needs robustness to adversarial markets. Science demands correctness and reproducibility. We'll discuss deployment challenges, data privacy, regulatory compliance, ethical considerations, integration with existing systems. By understanding domain-specific applications, you'll see how abstract AI concepts translate to real impact. You'll understand what makes deployment challenging in practice. Excellent work today. You now understand generative AI from GANs to large language models. You understand scaling, emergence, and limitations. You can prompt effectively and understand applications. See you tomorrow as we explore AI's impact across industries.